Now we want to talk about the idea of if I set up some kind of equation, how can I go about solving it, and what does that actually entail, or what does it mean? So really, we've been working with kind of statements. We've had these linear equations. And all that means is we have a statement that two things are equal to each other. So an equation is a statement that two quantities are equal. That equation can be true or it could be false. And to show you what I mean, I'm going to kind of use ones that make sense without any variables. So if I say 3 plus 2 is equal to 5, we know this is a true statement. The left-hand side is equal to the right-hand side. But if I say 3 minus 1 equals 4, well, that's not true. 3 minus 1 is 2. So these two are not actually equal to each other. This is a false equation. So what happens is when I set up an equation involving some unknown, which we typically use a variable for, we call that number that makes it a true statement a solution. Okay? And so our whole goal is to see if I were to replace this variable in whatever the equation is by this number, I get a statement that is true. The left-hand side is equal to the right-hand side. So we'll talk about what we do to actually solve linear equations, but just take a nice example. If I say x plus 1 has to equal 4, the only value that makes sense in that I plug in for x is 3, because 3 plus 1 is equal to 4. Nothing else is going to work in this equation. So here, x equals 3 is a solution to this equation. Okay? So this is your whole goal, figure out what value of x can you plug in. And when it gets more complicated, we'll just have to use more tools. But the whole idea is we're going to have four main things that we're going to do. You ultimately want to get the variable alone by itself. So we have all of these operations and there are ways to undo them. So if I have any kind of equation, we can add, subtract, multiply, or divide the same non-zero number to both sides, and it's not going to affect the solution in any way, shape, or form. So if I know 2 is equal to 2, when I add 1 to both sides, it's still going to make something that's true. And likewise, if you had an equation that's false, doing any of these to both sides of the equation is not going to change anything. It's very similar to how when we were talking about scaling up and scaling down, you could multiply top and bottom by the same thing, you could divide top and bottom by the same thing, and it still keeps the same core meaning. Exact idea here. And the benefit of this is if you think of addition and subtraction, these two operations undo each other. So kind of just going back up here, if I want to know what does x equal, what I can do is subtract 1 because plus 1 minus 1 cancels each other out. And that means I would do exactly the same thing on this side to get my solution of x equals 3. And then in exactly the same manner, multiplication and division go hand in hand because these two also undo each other. So we'll see some examples soon, but I want to kind of show you why this is the case, okay? So if I look at these different statements, 5 equals 5, we know this is something that is true, and 5 equals 10 is something that's going to be false, okay? So working with my first tool, if I add and likewise subtract the same number, it's not changing the core meaning. So if I go ahead and add 3 to both sides, what that tells me is then 8 equals 8, which still ends up with something that is true. So I have not affected the meaning of this statement. Where over here, if I subtract 3, I started with something that's false, and subtracting 3 still leads me to something that is false. So it has not changed the core value of my problem, okay? And likewise, multiplication and division do the same thing because we know these both go hand in hand. So if I start with the side that is true, if I go ahead and multiply this side by 2 and then do the same thing here, so remember parentheses or writing this x or even a dot indicates multiplication. 5 equals 5 is true, and in the same way, 10 equals 10 is still true. And over here, 5 equals 10, we know that's false. If I divide both sides by 5, 5 divided by 5 is 1, 10 divided by 5 is 2. I still end up with something that is false. Okay. So these are our 4 main operations that we're going to use in order to solve an equation. Now there is one kind of key thing here. Non-zero is super important. And really it's only important for multiplication and division. It does absolutely nothing with addition and subtraction. If you add 0 to both sides, it does nothing. However, multiplying by 0 can pose a problem, and we know we can't divide by 0. So it does make a difference in those situations. So just to kind of show you why we don't want to multiply both sides by 0. If I start with 5 equals 10, I know that's false. But if I go ahead and multiply both sides by 0, well, 0 times 5 is 0. 10 times 0 is 0. I now get something that's true. So I started with an incorrect statement, but now I ended up with something that is correct. So this is really important to us. We never want to multiply or divide by 0. Okay. So be extra cautious. Addition and subtraction, it's not going to do a single thing to, but in multiplication or division, it does pose a problem. So let's try a bunch of examples. We want to solve each of these equations, and there is the same goal in all of these. You want to get the variable by itself. The best thing you can do is practice, practice, practice. Try every type of example. We're going to start out kind of slow, and then we'll make it more complicated in the last couple examples when we have the variable on both sides of the equation, okay? So your whole goal is you want to isolate the variable. So starting with A, I have D divided by 360 is equal to 0.5. So my goal is to get this value of D on its own. I want to solve for it. So since I'm dividing by 360, the operation that's going to undo it is multiplication, because now these two will cancel each other out. But if I do that to one side, it means I have to take this other side and also multiply it by 360 to keep the meaning the same. But at least in doing so, now on the left-hand side, I'm just left with my variable D. And on the right-hand side, we need to figure out what is 0.5 times 360. So if you plug that into your calculator, or you can do it in head, you're looking for half of 360. The value of D that solves this equation is 180. So what I would tell you is while you're starting out with this, you should check your solutions. If it gets really complicated, it's a little bit harder to do so, but it's a good habit to get into. Because again, what this should do is lead to a true statement. So if I go back up here, let's get rid of all of this stuff to make it nicer. If I replace this value of D by 180, it should lead to an accurate statement. So going through that, our value of D is 180. If I take 180 and divide it by 360, it should equal 0.5. And if you plug that into your calculator, indeed, when you take 180 divided by 360, it is 0.5. So you end up with a statement that is true. If you make any type of error, this would be the way that you would be able to spot it. So it can be something small like a sign error, you added instead of subtracted, a bunch of different things could happen. Okay. Let's try this next one. We now have 4 times x equaling 2. And again, I want to get the variable on its own. So right now I have 4 times x. So the operation that's going to get rid of the 4 is division because they're being multiplied. So I'm going to take the left-hand side, divide by 4. And that means I need to do exactly the same thing to the other side. So at least in this ways, 4 divided by 4 cancels. And that leaves us with x. And on the right-hand side, we have 2 divided by 4. Now, if your directions don't say to put it in simplest form, this is a perfectly fine answer. But since both of these are even numbers, remember we can reduce this fraction, take top and bottom and divide it by 2. And so the reduced fraction for this would be 1/2, or that is a nice decimal 0.5. So either of these representations are good. Okay. So again, I could plug that back in the starting equation. If you do 4 times 0.5, it does indeed equal 2. Okay. Moving on to C, we have x minus 142 is equal to 70. And so I want to get x on its own. Currently, I'm subtracting 142. So the operation that will cancel it is addition. So I'm going to add 142, which means we do exactly the same thing over here. So at least this way, these two are gone. We're just left with x. And then if you do 70 plus 142, you get 212. So the value of x that solves this equation is 212. Okay. Moving on to D, we have n plus 1,361 is equal to 2,094. So to get n by itself, that's our variable, we need to get rid of the 1361. And since it's being added, we will subtract it to get rid of that piece. So all that leaves us with now is n on the left. And if you do 2,094 minus 1361, you should end up with 733. And so this is the solution to this equation. Okay. Now, when you start getting more complicated, if you look at these next two problems, there's multiple instances of the variable. It's still the same idea. You have to get the variable by itself. So if you noticed on all of these, you're isolating that x or whatever component it is. So I want to do the same thing. The problem is right now I have 3u plus 4u. So I don't have a certain number of u's on one side. So what I want to do is I want to combine these like terms because they can be combined. So we have 3u, we're adding 4 more. So in total, that leaves us with 7u on the left-hand side. And we've done absolutely nothing on the right. We've just combined the like pieces, okay? But now I've got all of my u's on one side and I have 7 times u. So to get the u by itself, we're now going to divide since 7 and u are being multiplied. That will make these two pieces cancel. And that tells us u is equal to 28 divided by 7. So our u is going to equal 4. So here's where it would get cumbersome to check. If you had to plug it in, you'd have to replace both of these u's by 4. So it's definitely a bit more tedious, but still doable. Okay. Now for this next one, we run into quite a bit of a problem. Because if you notice, we have an x on the left-hand side and an x on the right-hand side. So if you look at all of these past ones, what we've ended up doing is we've got the variable on one side, the constant on the other. Variable on one side, constant on the other. Variable, constant. Same thing is going to happen. I'm just going to have to do some work to be able to move all of my x's to one side over here, because I want to get all of the terms involving x to one side. The problem is I can't just move this x over because I've got these parentheses to take care of. So if you think about your order of operations, you could try to subtract x, but I can't do subtraction before I get rid of parentheses. So this isn't going to be my best first step. Instead, using my order of operations, we can get rid of the parentheses through multiplication. And that's going to make things a little bit easier to work with. So remember, this is that distributive property. We go ahead and multiply the 4 to both pieces. So we have 4 times x, and then we'll do 4 times negative 3. You can write it all out if you need to. So that distributes as multiplication. And then we've done nothing on the right-hand side. And then just multiplying those two pieces to make life a little bit easier. 4 times 3 is 12. In reality, you can skip this intermittent step. You distribute that 4 out as multiplication, and you don't have to write everything out. Okay. Now at this stage, it's looking a lot better, but I still have x's on both sides, and I still have a constant on both sides. So you can go about this whatever way you want. You can start by moving constants over, but I think the easier thing is start by moving x's. You've got more over here, so it's going to make more sense for me to bring this x to the other side. So right now we're adding these two together. So to move it over, I'm going to subtract it. So 4x minus x gives me 3x. And then I've done absolutely nothing with that 12 or that 10, but at least the x is gone from this side. Okay. And now I'm getting close. Again, I want to get the x by itself, but we've got this minus 12 in here as well. So to move that to the other side, we're going to go ahead and add it. That way these two are gone. So now I'm left with 3x on the left, and then 10 plus 12 will lead me to 22. And now I'm super close. To get rid of the 3 that's out front, we go ahead and divide by 3. That will make this disappear. We're then left with x. And unfortunately on the right-hand side, if you do 22 divided by 3, you're going to see it's not a nice number. It's going to keep repeating over and over and over. So in this case, it's going to be best to leave it in this form, okay? Unless the directions told you to round to however many decimal places. But this is that actual number solution. So we don't like approximations if we don't have to, okay? So it's going to take a ton of time. Get as much practice as you can with this, because this is a very important concept moving forward. The whole goal, though, is just isolate that variable. There's going to be different approaches, different ways. You can do a lot of different things to get to the right solution, but just keep your order of operations in mind, and keep in mind what is going to cancel those operations out. So one of our main focuses, though, is if I have an unknown in some kind of problem, or even in just my daily life, I can go ahead and I can set up some equation to actually solve it. So if I have this unknown, if I can create the equation, I then can isolate my variable in the same way. So let's try a couple examples. Milan ordered some books online and spent a total of $75. Each book cost $6, and he paid $3 for shipping. We want to figure out how many books did he end up buying. Okay? You don't need an equation to do this, but let's try to write an equation that can be used to answer the question. And since what we're searching for is how many books he bought, we're going to use the variable B to represent that. That's our unknown, okay? So just thinking about this in a normal, everyday manner. If you order something online, your total cost is going to be the cost from purchasing the books plus however much you had to pay for shipping. That's some fixed flat fee. Okay. Now the cost of books depends on how many books you buy. So what this is actually equal to is it's the cost per book multiplied by the number of books you bought. Okay. And then we go ahead and add the shipping. So filling in all the components for this, my total cost is $75. The cost per book is $6. We bought B books. And then we have to add $3 for shipping. Okay? So this is going to be my equation that represents this situation. Right? And again, it's just a matter of breaking it down into those logical pieces. My total cost is the cost per book multiplied by the number of books to give me the total cost I spent, plus that $3 we had to spend shipping. Okay. So my goal now is, what value of B do I plug into here to make this a true statement? So we're going to go ahead and now actually solve this equation. So we want to isolate the value of B. So again, I've got 6B plus 3. I don't want to divide yet because I don't really know how to talk about division of something with addition here. So instead, get the stuff involving B on its own. So let's go ahead and subtract 3 from both sides to make those two cancel. And then 75 minus 3 is 72. And we're just left with 6B on the right. And now I have a nice simple equation that I can go ahead and divide both sides by 6 to make those cancel. So if you do 72 divided by 6, you will get 12. And that is equal to our value of B. So this is how many books we bought in the bookstore. And again, this isn't 100% necessary to set up this equation, but again, it's a good habit of getting into. If I thought about this in a different manner, my total cost is $75. I paid $3 for shipping. So really that means I spent $72 on books because I just subtract the shipping off that total. Well, if I spent $72 on books, I'm going to divide it by 6 because that's how much each book cost. And if you do 72 divided by 6, it's exactly 12. So it's really these steps that you're taking anyway, but you can do mentally in your head or with a calculator instead. Okay? So it's good to get practice with equations like this and problems like this because it's a lot nicer. However, a lot of times things aren't going to be as clear-cut. So let's try another example where it's going to see that we have a little bit easier of a process going through setting up an equation instead. So we're told the residents of a city voted on whether to raise property taxes. The ratio of yes to no votes was 4-5. If there were 3,408 yes votes, we want to figure out what is the total number of votes. So there is a lot of information going on in here, and we have to be really, really precise about what we label our different pieces. So if you think about, we're searching for the total number of votes. The total number is equal to the number of yeses plus the number of noes. Okay. We have this, but we have no idea what the number of no's is yet, okay? However, they do give us this piece of information that the ratio of yes to no votes was 4-5. So if you remember, the word ratio is going to indicate that we have some kind of fraction. So yes to no's is 4 to 5. So what that means is I can write it as a fraction, 4 to 5. This is the number of yeses. This is the number of no's. Okay. And what I want to do is I want to set up an equivalent equation on the other side, keeping the same information aligned. So in the top, I want something dealing with the number of yeses. And in the bottom, I want something dealing with the number of no's. Now, I don't know what that is. So in the denominator, I'm just going to go ahead and call this x. Okay? It's my unknown. You can use n as well as you want. Really doesn't matter. Okay? But now the number of yeses, we are told it's 3,408 votes. So our whole goal is to figure out what is the value of x that solves this equation. So I'm going to show you another technique that you can use to solve stuff. It works really well when we have fractions like this. You don't need to go about this process though. Your goal is to get x by itself. So you could go ahead and multiply both sides by x to get it out of the bottom. But I think what happens is when you have fractions and fractions and fractions, we really don't like them. So we're going to use a technique called cross multiplication. So I've got two fractions equal to each other. So I'm going to go ahead and cross each of them. And so what that does is I'm going to multiply those cross components. So 4 and x are going to get multiplied together. And then 5 and 3,408 are going to get multiplied together. So we're multiplying those cross pieces. Okay. And now it leaves a cleaner equation that I can solve for x. So if you go ahead and do 5 times 3,408, you will see that this is 17,040. And then to solve for x, you have 4 times x. So we're going to go ahead and divide both sides by 4. And so what that tells us, 4 divided by 4 cancels, and that leaves us with the unknown x. And if you do that division, you get 4,260. And so x is representing the number of no's. This means there are 4,260 no's. So you think at this point you're done because you got an answer for x. But again, this doesn't go back and actually answer the question. This told us how many no's there were. So this means our total number of votes is going to be the number of yeses, which is 3,408, plus this number of no's, 4,260. So adding these together gives us a grand total of 7,668 votes. Okay. So be super, super, super careful on what the question is actually asking you. Just because you found a solution to the equation doesn't mean you answered the question. The other thing you also want to be doing while you're going through this process, and this is something that doesn't have a fix, but you should be asking yourself, is this plausible? So at this stage, if you found that there was a half of a vote or 0.3 of a vote, you know that doesn't make sense. It has to be a solid whole number. So it doesn't tell you where you went wrong, but you know what process you went through didn't actually work. So you have to try something else instead. And so we'll go through techniques later on where we'll talk about how we can solve problems, but it's something we just need to get in a practice of. Does this solution actually make sense?